Hi, this is Open Up Resources with Algebra 1, Unit 2, Lesson 5, Twin Powers. I'm going to review some of our exponent rules today and see if we can find some connections between yesterday's fractions and in-between points and those exponents and what we've been learning. So going on in here, the jump start, we want to illustrate with an example of why these work. So I'm just going to use, let's get on the right thing here. So I'm going to do a to the third times a to the fifth. So I'm multiplying the same bases. So I'm going to add the exponents. A to the third times a to the 5. Actually, let's even go one step further on this. I have a times a times a times a, 3, 4, 5, right? So in total, I have a to the 8th. I have 8 a's, which is what 3 plus 5 is, right? All right, the next one. I have, let's do 3 and, now we'll do 4. A to the 4th to the 5th. So when I'm taking an exponent to another power, that's basically saying a to the 4th 5 times, which we just said above, that we add all those together. Well, that really looks like it's 4 taken 5 times, which is a multiply. So that's a to the 20. Why this isn't writing? Okay. Next one. So we add exponents, we multiply exponents. Now when we divide numbers of the same base, we are going to subtract. Let's prove that. So I'm going to do a to the 7 divided by a to the 3rd. That's what that looks like, is I have 7 a's in my numerator. 3, 4, 5, 6, 7. Why I'm not there. And 3 in my denominator. And when we do those, they actually cancel each other out, right? So it's like I have 7 and I take away the 3 that are on the bottom. So that's a, taking away those 3, and that's a to the 4th. That's what's left. My 4 up here. Okay, the next one. A times b to the m power. So if I have the same exponents, the bases can be multiplied. So let's just do a times b. Let's do to the 3rd power, which means I have ab times ab times ab. Well, multiplication is commutative, so I can rearrange these however I want. So I'm going to put all the a's together and all the b's together. And so there we have a to the 3rd times b to the 3rd. Okay. And our last one, how we can distribute these as well. Let's just do to the 3rd again. We'll go ahead and go back to that. So a over b, and we'll put that to the 3rd power. So what that looks like is a over b times a over b times a over b, which we know we just multiply those a's together. So that's a to the 3rd. Multiply the b's together, b to the 3rd. So it's almost like a distributive property. You're distributing the exponent to each of those numbers. Same above. It's like you're distributing the m to both of those bases. All right, so summarizing this. What if we have the same exponent on there? A to the 3rd divided by a to the 3rd. By our rule up above, which color did I use? 3, I did pink. Okay, so according to that rule, I would do a to the 3 minus 3, which equals a to the 0. And so anything let's see, and a to the third, by dividing out common factors. So a to the third divided by a to the third, it's the same number. It's like 5 divided by 5. Your answer is 1. So by conclusion, we can say a to the 0 equals 1. Okay, the answer to this one equals the answer to this one. All right, let's try it with this one. So also by rule 3, I'm going to go ahead and use a different color so we don't get confused here. We subtract. So a to the 3 minus 4 equals a to the negative 1. And if we divide out these common factors on here, remember we have 3 a's on the top and 4 a's on the bottom. If we cancel out, I'm left with a 1 on top and an a on the bottom. It looks like an a and not a 9. So therefore, we can take our two answers and say a to the negative 1 equals our other answer, 1 over a. Okay, so just those are rules you should have learned last year, but just in case, that's kind of some more proofs on how we got there. Let's go ahead and scroll down here. So we are going to relate these key features of exponential functions and the properties with negative exponents. We're going to focus on negative exponents today. All right, so Carlos and Clarita have been working on their math together and noticed something interesting. Carlos has been looking at the graph of f of x equals 2 to the x power, that's right here, on my calculator and trying to make sense of the graph. When the inputs are negative, here's what I see on the graph. So here's going into the negatives. What's happening? What observations are we seeing? Well, I'm seeing on here, especially when the x values are negative, I'm seeing that the function is always positive y values, right? We're staying above 0 on here. It looks like we're getting really close, but we're staying above. Notice it increases from left to right. That's how we read a graph. Left to right, we're going up. And if we go left, though, the left, the values, the y values, oh my goodness, get closer to 0. Okay, so those are some of the things that I noticed on here. Clarita says it sometimes helps to make a table and look for patterns in the numbers. So she's going to do that. So Clarita's doing a table on this next page. Let's go ahead and fill it in. Let me go ahead and get back to this one. So if I notice here, I'm going 16, 8, 4. I'm dividing by 2, right? Or timesing by 1/2, because that's a common ratio. We're looking for the multiply, so times 1/2. And so if I take half of 1, that's 1/2. If I take half of a half, that's a fourth. Half of a fourth is an eighth, and half of an eighth is 1/16. Okay, so she's looking at that and doing, okay, well, what if I do the common ratio of 1/2? What happens there? So notice here's what the graph looks like compared to the other one. So if we compare the two graphs, what do we notice? Well, I notice that it's a reflection over the y-axis compared to the other one. The other one went down this way across. This from left to right, it went up. This one is going down from left to right. So you might say it's kind of an opposite. And I'm going to put on that decreasing y values decreasing from left to right. Okay, those are some things we can we can see on this guy, kind of the difference. Okay, so let's compare this table that we were just doing. So here I'm going to fill in the ones from before, right? Oh, not 1/2 again. We're multiplying by 1/2. So a 4th, an 1/8, 1/16. Okay. So now if I'm looking at this one up here, I can see that when I'm at 4, oh, it's pretty low. Let's start at the negatives. So -4 looks like it's at 16 over here. And when I come down to -3, it looks like it's at 8. And -2 looks like it's at 4. -1 looks like it's at 2. 0 is still at 1. And now I start going, let's screw this up so I can write easier, to 1/2, a 4th, 1/8, 1/16. So going this way, it's a times 2, isn't it? Which is actually the down, right? So I'm taking it 1/2 each time as I'm going backwards. On there, they kind of wrote the table. Normally, we put the negatives. Normally, we put the negatives on this side. So this is kind of opposite of what we would normally write our table. Okay, what similarities and differences do you notice in the table values? How can you explain that? Well, I'm going to look at these. So I notice that it's kind of opposite on here. It looks like the opposite x values are answers are reciprocals, the reciprocals of each other. And, undo. And kind of seems like 1/2 to the x power. So if you look at this, if I put these all in powers of 2, over here, it's actually 1/2 to the 4th power. This one is 1/2 to the 3rd power. This is 1/2 squared. So notice how 3rd power, 2nd power, 4th power, how that kind of goes over here. So let's write this all down. I'm going to go ahead and put this together over here. How would we explain this? I'm going to say opposite x value answers are reciprocals. Okay. And then I notice that both have the point 0, 1. And then I'm going to, let's write this other one kind of by hand. It'll be easier. So 1/2 to the x power is the same thing as 1/2 to the x, which we actually proved on the jumpstart, right? We distribute that to each of them. Well, 1 to any power is still going to be 1. And so we just distribute the x down to the 2. Okay, so Carlos, I remember this about negative exponents. A to the negative n equals 1/a to the n. So negative exponents always have a twin. The equivalent expression is written with a positive exponent. So if we're going to get rid of that negative exponent, we do the reciprocal and make it positive. So explain how Carlos remembers about negative exponents relates to the relationships you've observed in those up there. So it's a little bit of a mouthful. Let's go ahead. How does that relate? How do we know they go together? So the y values of inputs with negative exponents are the reciprocals of the y values with positive exponents. So let's just look at that. The y values of the inputs with negative exponents are the reciprocals of the y values with positive exponents. So Here's my negative exponent. These are reciprocals of each other, right? This is 1 over 2 to the first. This is 2 to the negative first. Here I've got 1 over 2 to the second, which is also 2 to the negative second. Here's 1 over 2 to the negative third, same thing as 2 to the negative third. So just kind of how you're looking at that. So they're opposites that way. It's kind of a weird thing to try to explain. Okay, so trying the multiplication rule for the exponents of adding the exponents when the bases are multiplied to these expressions. When you finish, use another method to verify your answers are correct. So how we're going to do this is I'm going to go ahead and do one proof in one color, and I'll do the other proof in another. So our rule says we're going to add the exponents. So 2 to the 5th minus or plus a negative 3. I should put it like that. Plus a negative 3, which if I have 5 and I'm adding a negative to it, I end up with 2 to the second, which is 4. But below it, I'm going to put what these actually are. So 2 to the 5th is 32. 2 to the negative third, so that's basically 1 over 2 to the third, which is 1/8. Well, 32 times 1/8, or 32 divided by 8, is 4. So see how those both got the same answer. Okay, let's try it again. So 3 to the second plus a negative 2 equals, so that's 3 to the 0, right? 2 plus a negative 2 is 3 to the 0, which we know of equals 1. So if I'm going to do this, 3 squared is 9 times 3 to the negative 2 would be 1 over 3 squared, which is 9. So a ninth of 9 is 1. Okay, next one. Let's do subtraction or division. So if we divide same bases, we subtract the exponents. So I'm going to do 3 to the second minus a negative 1. Don't forget those double negatives in there. Minus a negative is the same thing as plus a positive. So that is 3 to the third, which is 27. Now if I write this out, 3 squared is 9 divided by 3 to the negative first is 1 over 3. Now remember, when we division is the same thing as multiplying by a reciprocal. So 9 times the reciprocal of 1/3 is 3. That gives me 27. Oh, I didn't use a different color for that. Whoops. 9 times 3. There we go. All right. Next one. Let's try it. 5 to the negative second plus, not plus, minus, we're subtracting our exponents, minus 3. So I'm getting farther into the negatives, 5 in the negative fifth, which would be the same thing as 1 over 5 to the 5th, which is the same thing as 1 over 3,125. Okay, now 5 to the negative second is negative 5 squared on there, divided by 5 to the third, which is 125. Now remember, division is multiplying by the reciprocal, so my first one stays the same. Then times by 1 over 125, which is 1 over 3,125. So they match. Next one. So this is where we multiply the bases. So 3 to the third times a negative 2 equals 3 times negative 2 is negative 6, which equals 1 over 729. Now 3 to the third is 27, and if we do that to the negative 2, that equals 1 over 27 squared, which equals 1 over 729. You can double check that all in calculators if you don't believe me, but it works. Okay, so 1/5, Wait, this one's supposed to be with the rule. 5 to the negative 1 times negative 2. Negative times a negative is a positive, so 5 squared equals 25. And the next one is 1/5 to the, let's scoot this over, I'm getting crowded. They don't give me a whole lot of space on this. 1/5 to the negative 2. Well, 1/5 to the negative, the reciprocal, would be 5 to the positive 2, and that equals 25. All right, so there we go. We have practiced those rules. Biggest thing is just making sure you remember how to work the negatives. All right, so Carlos has already written the rule for negative 1/2 to the x for this function. What is the other rule he is thinking about? So if you were to, basically, I'm just going to rewrite this. G of x equals, and I'm going to put the parentheses on here because if technically we need to have the parentheses involved, otherwise it's 1 to the x, and that doesn't do anything. So the other rule that they're talking about is, what's the reciprocal of that if I'm going to use a negative? So if I want to switch those around, I can do 2 to the negative x, and that those both should make that graph. And we can double check that on Desmos. I'm not going to do that right now. Okay, 10. Can you write two different rules for this function? Well, if we look, it's the opposite of this. So I'm going to start with my f of x equals 2 to the x, right? 2 to the first, 2 to the second, 2 to the third, 2 to the fourth. So then my second one would be the opposite, which would be 1/2 to the negative x. And those both should make that graph. So those are the same things. So Clarita says, wow, that's interesting. So how can I tell if an exponential function is always increasing or always decreasing before I graph it? How could we answer her question? Well, for f of x, equals a to the x power is increasing if, so a to the x right here, it's increasing if a is greater than 1, right? It's greater than 1, and decreasing if a is basically between 0 and 1. The same thing is true if we do g of x equals a to the negative x. Oh, a to the negative x, there we go, is increasing, or is decreasing, sorry, we'll start with that, is decreasing if a is greater than 1, and increasing if a is between 0 and 1. So when x is positive, we know it's increasing as we're going left to right. If x is negative in our exponential, it is decreasing from left to right. Okay, let's the ready for mores. Actually, I'm going to do those real quick because they are not too bad here. Negative 3 to the negative 2. We can rewrite that as negative 1 over negative 3 squared, which is 1/9. The next one is negative 3 to the third. So it'd be 1 over negative 3 to the third, which is negative 1/9, right? Because if we multiply 3 negatives together, we get, or not 9th, 27th. 3 times. I forgot to do 3 times. 27th. And if we do negative, let's do this one in green. And so if we do negative 3 squared, remember the exponent only goes with the number. The negative is actually times -1. So then my answer would be -1/9 because I'm going to do the squared and then take the things first. Negative before, or an exponent before negatives. All right, so what would happen if you tried to use the base of -3 on your graph? I think this one's kind of interesting. So I'm going to go ahead and just do that on here. If I put my line in here, just try to put it right in the middle. And I'm going to go by kind of a weird 1, 2, and then we'll do 3 up here. And so this is -1, -2, -3. Oh, wait a minute. You know what? I want to do them a little bigger because ninths, because isn't, let's do this a little bigger. 1, 2, 3, 1, 2, 3, and then 1, 2, 3, -1, 1, 2, 3, -1, 1, 2, 3, -3, 2. And then I'm going to go 1, 2, 3, 4. 1, 2, 3, 4. Okay. So if I threw in a -1, so -3 to the -1 power, we said was a -3rd, right? -3 is -1/3 for my answer. But then if I do -3 squared, it was a positive 1/9. So the -2 was a positive 1/9. Oh, wait, that's too high. Wrong direction down here, 1/9. Wow, I'm struggling today. Let's try this again. This was the -3rd. This was the positive. So then this one was the -1/27th, which is really close to the line. If I do 3 to the 0 power, I get a 1. If I go -3 to the first power, it's a -3. What's happening to our line? Our function jumps between positive y values and negative y values and wouldn't be continuous. All right, so that's just kind of a neat thing to look at. All right, so for our takeaways, what did we notice? We noticed there's just these couple here. Yep. Okay, so I noticed several useful strategies working with exponents that are negative. So what I noticed was we can rewrite negative exponents as positive exponents by replacing the base with its reciprocal. Okay. So if we have that, we don't want to use the negative exponents, we just make the reciprocal and then our exponent can be positive. I noticed several things about exponential functions over the past few days. Each of those observations can be supported by the properties of exponents. Okay, so what that means is exponential functions are continuous with rational inputs We also know that f of x equals a to the x power, and g of x equals 1 over a to the x power are reflections across the y-axis. And vice versa, right? So let's see, can I fit that in here? Let's scoot this guy over here so I got a little more space. So then f of x equals a to the negative x, and g of x equals 1 over a to the x are reflections across the y-axis. And last but not least, end behavior is an asymptote. So I'm going to write these all down here so we can actually read them all. Okay. So this information goes right in here. So that's what we ended up with. Thanks for joining us, and we will see you next time.